Okay, I'll first wait a few more minutes to see if anyone else would join. We'll probably start at around 6:33 or 6:34. What? Yes, so why are you calling?
Okay, start, okay?
Nice. I apologize for the interruption. I guess since I'm not so sure if anyone would come here, uh, I, I don't think anyone else is gonna come in like the foreseeable like few minutes. So I'm gonna start the lecture. Today is basically going to be a basic introduction to kinematics. Kinematics is basically the study of motion, or just studying moving objects, and most commonly how their velocity, acceleration, time, and position vary. So today we're just going to go over like the very basic concepts, like the most basic parts, just starting from the ground up. And by the end of the lesson, we will basically get to some of the basic kinematic equations. So like the fundamental kinematics equations, and maybe do some practice problems along the way. Okay, so kinematics, as I said earlier, is the study of motion. And what is motion? Motion is a state like an object or matter is in, and motion is basically indicated by a change of position over a period of time. So we can normally measure motion using displacement, which is literally a change in position. So you would have an initial position, or the position an object begins with, and a final position, which is the position the object ends in. And over a period of time, this object would travel from the initial position to the final position in some way. We don't care what way, but it would always travel in some way from an initial position to a final position if it's in motion. And the distance between these 2 points would form a line. So these 2 points would form a line, and or a vector if you want to get really technical, and then that's called your displacement. So what is a vector? A vector is basically a quantity that is described by both a magnitude and a direction. They're normally denoted on graphs as an arrow. So the bottom of the arrow, the one without like the head, is basically your initial position. So if you look at this graph below, this is a 2D coordinate plane, which you might have seen from your math class. Vectors most commonly come out from the origin because then it is very easy to describe like where the vector is headed. So for example, for this vector, you could see that relative to the axes, if the object which that traveled vector r traveled rx, a length of rx right, and a length of ry up. So we can denote this vector as rx, ry. This is basically kind of like how your coordinate system works, and it's very similar in some ways. But what makes a vector very unique is basically its magnitude. It has magnitude and direction. So those two are put together. Now, things that just have magnitudes are called scalars. So these tend to be like absolute numbers, and commonly they basically just span positive numbers. They only have a magnitude. You cannot possibly say that any kind of measurement that is measured with scalars, that's basically a scalar, you cannot say that they have direction. So examples of both, like scalars and vectors. Scalars are like things such as mass, since mass doesn't have a direction, and also it cannot be below zero. Temperature, even though this could be below zero, you cannot say temperature has direction. It is just pressure is also a scalar. Work is not in here, but that's also a scalar. Electric charge, speed, and a bunch of other stuff. Vectors, examples of vectors include force, velocity, momentum, and other things. So we kind of went over this in the last slide, like what displacement is. Now, a very common mistake that some people tend to make, like especially in like introductory physics classes like physics 1, is that they tend to mistake displacement versus distance in like word problems and write in like problems that require like either one. The same can be said for like speed versus velocity, although colloquially, we tend to use these terms interchangeably. They do not mean the same thing here. Displacement is basically a vector that represents the change from the object's initial position to its final position, and the magnitude of that vector would be called a scalar. Now, that would be kind of, that's really technical as like a difference, but and I guess an easier way of to think about it is that imagine if we again started off with from an initial point, let's call it I, and then we end in a final point O. But let's say we took like some weird path, like a meandering path that went like this way. So here, distance is the length of the path you took. So it is the length of this curly, weird looking path. But the displacement is basically unrelated to this path, and it's just simply if you were to measure the displacement, it would just be the length of the line that connects these 2 points. Another example is a circle. So imagine you are running on a circular track from like some point, and you run 1 lap, and the circumference of this circular track is 200 meters. What would be the displacement and distance if you just run exactly 1 lap? Then your distance would be 200 meters because you ran a total distance of 200 meters, but your displacement would be 0 because you ended up in the same point where you started. So there would be no change in position in that way. So we can do this knowledge check. So the diagram below shows the position of a cross-country skier at various times. At each of the indicated times, the skier turns around and reverses the direction of travel. In other words, the skier moves from A to B, and then it moves back from B, it goes to C, and then it moves forward from C to get to D. So determine the displacement and the distance traveled by the skier in the 3 minutes that they took to move from A to D. If you want, I could give you time to solve this for yourself, but I could discuss the solution right here since there's other stuff to cover. There's quite a lot of other stuff to cover as well. So if you want, you could put your answers in the chat on like what is your displacement, what is the distance that the skier traveled. If not, I'll wait a couple of minutes to see if any responses pop up, and then at around like 6:45, I will discuss the answer. My computer is behind in time, actually. This is not very accurate. Sorry. Sorry. I think most people got that the displacement is 140 because from the only things that matter when you're considering displacement is the first and final position. And we know from the problem that the first position is A and the final position is D. So you just add up the two lanes here. For distance is a bit harder because you have to add up the individual segments that the skier travels to get to get between each of the 4 points. So from A to B, the skier has to travel 180 meters from the 40 plus 100 plus 40. And then from B to C, he has to travel another 140 meters because that's the distance between B and C here. And then from C to D, that's another 100 meters. So now if you sum up those 3 lanes, that would be 420 meters. I'll go over this one very quickly, but it's pretty much the same type of question. So basically, there's a football coach that's pacing back and forth along the sidelines. And again, the coach is moving from A to B to C to D in 10 minutes. So the displacement would just be the difference from A to D, which as you can see here, that's about 55 yards. And then from A to B to C to D, you have to add up those individual like distances between those 2 points. So you get 95 yards for the distance. Okay, so speed and velocity, similar to how distance and displacement are different, speed and velocity are also different. So speed is basically just how fast something is traveling. It does not have a direction. Speed is a scalar. Speed and velocity are related in the same way that distance and displacements are related because of the formula for speed, which you guys might have learned from like your math class, that speed is equal to distance over time. Similar to that, velocity is equal to displacement, like a change in displacement over time. So here we call this average speed because it's over a stretch of time, and obviously it doesn't have to be constant and over that stretch of time there could be acceleration and stuff. So if you're really just looking at the difference of distances, like the distance traveled over time, that is your average speed. This is contrasting with the instantaneous speed, which is basically a type of speed you will see in like more advanced physics, in which that's basically the speed something is traveling at a certain moment, and you have to use calculus to get that. So I think the main thing you should remember from this is that speed is a scalar quantity that cannot be negative and is just equal to distance over time. Velocity is a vector quantity that is equal to the change in displacement, is basically equal to displacement over time. Yeah. For those of you who know calculus, as Ryan said, as one person put in the comments, the specific thing you use to find like instantaneous velocity is the derivative. So you have to take a derivative of your position equation, but that's beyond the scope of this, since the math there is hard. So, oh, okay. And acceleration is basically how like similar to how velocity relates to position. Acceleration is a change in velocity over time. So if you if you were initially traveling at like 1 meters per second and you sped up to 2 meters per second in like in 1 second, your acceleration will be 1 meter per second squared on average during that second. Okay. You can see because velocity depends on direction since it's a vector, the velocity of an object can change even when the speed remains constant. So this is kind of just like an example of how vectors and scalars can be very different. And this is very important to take note of because in questions where you're asked to draw the velocity vector, especially when you start getting into rotational motion, you have to pay close attention to like what direction is the velocity heading, because if you do not like put that down correctly, if you do not like pay attention to that, you could get the entire problem wrong. Okay. So a simple question that uses like velocities is this. So a boat is in a 1,000-meter race and it crosses the sun at its full flying within exactly 1 minute and 20 seconds. Determine the velocity of the boat in meters per second. So here you're using displacement. So the initial position would obviously be at the velocity line. You can just say this point is the 0 point. And then we know of the course 1,000. So finish line, the final position would be at 1,000 meters. And then we know that the total distance traveled is 1,000 meters. And then the total time that you take to complete this is 1 minute and 20 seconds. But for sake of simplicity, we will just say that in seconds. So 1 minute is 60 seconds. So 1 minute and 20 seconds is 80 seconds. So to find velocity, you just do the change in position, which is the final position minus the initial position divided by time. So that's 1,000 over 80 or 12.5 meters per second. So this is your average velocity throughout the entire race. It does not refer to anything regarding your instantaneous velocity. Basically, this basically just reveals your average velocity. It does not reveal anything about like how fast you're traveling at. For example, at the 400-meter point, that could be anything from if that's all we know. Okay, a submarine descends 150 meters in 5 seconds. Find the velocity of the submarine. So then again, you can do the same thing. The distance traveled is 150 meters, and the time takes 5 seconds. So your velocity is 30 meters per second, like down, if you want a direction. Okay. Another question that that uses something like this is a roller coaster. So as a roller coaster car starts down a slope, its speed is 4 meters per second. But 3 seconds later at the bottom, its speed is 22 meters per second. What is the average acceleration? So you do basically the same thing as what we did for the average velocity, but instead of taking the differences between positions, you're taking the difference between velocity, because acceleration is change in velocity over time, or the rate of change of the rate of change. So the initial meters per second, the final speed is 22 meters per second. What if you subtract these two, you get 18 meters per second, like as an increase in speed or velocity here. So then we know your time is 3 seconds that you took to increase your speed. So your average acceleration would just be 18 over 3, which is equal to 6 meters per second squared. Note that we have to use per second squared here because the units have to match up. So we know that if you multiply time by acceleration, you get your change in velocity. And when you multiply that, you get your change in position. So your units have to accurately reflect that. So if you multiply this by a certain number of seconds, like one of those units, if you can visualize, if you could imagine this would kind of cancel out with one. So if you multiply your acceleration by time, you'll get a velocity, which is in meters per second. So that would get rid of one of these seconds. Another way to think about it is meters per second per second. So that's your change in meters per second per second. Apologize if there's any technical issues. Although I'll try to go slower. A satellite's original velocity is 10,000 meters per second. After 60 seconds, it's going 5,000 meters per second. What is the acceleration? We can say that the final speed is 5,000 meters per second, and the initial speed is 10,000 meters per second from the problem. And we know that takes 60 seconds to slow down. So you can do the same thing. Make sure to put 5,000 meters per second as your final velocity. The order matters here because it's subtraction. 5,000 minus 10,000 and then divide by 60 gives you negative 83.33 meters per second squared. This negative sign in front shows that the thing is decelerating. That means that the change in velocity is negative. This is okay to do because acceleration, just like velocity, is a vector, not a scalar. So it doesn't have that kind of numerical restrictions. You can use our newfound knowledge of what velocity, acceleration, and time, and all that stuff, and we can define some basic equations that relate to these three. So when you're taking your physics class, these are basically your equations that will come up a lot. So the first one is relating your speed at a moment, and you're relating that with initial speed, acceleration, and time. Keep in mind that for all of these equations, but down below, you are assuming that your acceleration is constant. If your acceleration is not constant, you cannot use these equations. Okay, so for the symbols, you can read the ski here, but I'll explain all of them. So V here does not refer to velocity as a general thing. It refers to you can think about it as VF or final velocity, but it's if velocity after some point of time has progressed since something has been accelerating. V0 was your initial velocity before the thing started accelerating. A is obviously acceleration, T is time. Delta X is basically the symbol we use to delta X or delta Y is basically the symbol we use to denote displacement. The delta here symbolizes a change. So this literally just means a change in X or change in position. I would say the two most important of these four that you have to know are the first and third one. So this first one says that your velocity after some point is your initial velocity plus acceleration times time if acceleration is constant. You can think about it as like a graph. So imagine we are plotting like t here, and let's say v0 is 0. So we will plot v here. So since the acceleration is constant, actually your v would increase, like the rate of which v increases with respect to t should be constant, so there should be a line. So in order to get it, you just say that this is basically your rate of change times t, and then that'll get you a point at some point. So basically, this, you could say this is equal, if you say, sorry, you could say the slope of this line is acceleration since the rate of change of velocity is constant, and the equation, the equation for this line, since here we're just like assuming that v0 is 0. If it's not, you could just shift it up and down as you would like. But here it will be y equals ax, or here v equals at. So, and if you shift it up, this means that you just started at some velocity greater than 0. The same concept applies. The other one is this one. So delta x, your displacement, is equal to your initial velocity times t plus 1/2 of at squared. So this might be a bit harder to understand, but unless you know like calculus and you know that like the antiderivative is the area under the curve. But basically what this is saying is that if you have a velocity, if you know a lot about your velocity and you know like, and you have this graph, you can just drop a perpendicular down where you want at for this like t value, and the area of this trapezoid would be your delta x. I would say it is best to just memorize these two like by heart, because you'll be using this a lot, like a lot. So it would be very inconvenient to have to refer to an equation sheet or like look it up to like remember these equations. All of these equations have like some variable that is substituted out. That's why we have like a different thing. So for example, here there is no final, here there's no t, and then here there is no a. So, and then here there's no delta x. So each of these equations has some variable that is switched out, that basically it doesn't really tell, it's not relevant and doesn't really tell you anything about like that variable that was switched out. So it's important to use the appropriate thing. It's important in problem, if you're given a problem that needs you to use like, that needs you to refer to like the kinematic equations, that you properly assess like which variables are you given and which equation should you use to find your unknown variable. Okay, so might have to, if you want to solve it, you might want to take out your calculators for this one, because the numbers aren't that great in terms of like being able to do it mentally. But let's say a plane accelerates down a runway at 3.20 meters per second squared for 32.8 seconds until it finally lifts off the ground. Determine the distance traveled by this airplane before takeoff. Since here this airplane is just traveling in one direction, your displacement is basically the same thing as your distance in terms of like the numerical value. So we will, since we are given, this is acceleration, since you could tell by the meters per second squared, this is acceleration, this is time, and we know that it just starts accelerating down the runway. So that means it starts from a rest. Like if you like recall, like an airplane taking off, it starts from rest and accelerates rapidly until it takes off the ground. So that means that the initial velocity, even though it's not like explicitly stated, but we can reasonably assume that the initial velocity is 0 meters per second. It starts from a standstill. So here you would use that you would use your third kinematic equation. So your displacement is equal to your initial velocity times t plus 1/2 of at squared. Since this initial velocity is 0, you just get rid of that and just say that your displacement is 1/2 of AT squared. So if you substitute in your values, you could get rid of this like first term and you just get, this is 0.5 times 3.2 meters per second squared times 32.8 seconds. And then you have to square that. Here, your units would cancel out. So this is important to note that like once you finish your problems, your units have to be in check. They have to be able to like reasonably like trace back to each other. But if you throw this in a calculator, you would get that the displacement is about 1,720 meters. Example 2. So a car slows down its motion from 10 meters per second to 6 meters per second in 2 seconds under a constant acceleration. What is its acceleration and how far did the car travel during this time interval? So we know since this is under constant acceleration that we can use our kinematic equations. I need a water break, so excuse me. We know our V initial is 10 meters per second because of the problem, and we know V final is 6 meters per second. We also know our time, t, which is 2 seconds. So to solve part A, what is this acceleration? Recall that the first kinematic equation stated that V is equal to V0 plus AT. You can do substitution to say that AT, you move the V0 over, so you can say AT is equal to V minus V0, or basically just the difference in velocity. And then to find A, you would divide by T. So you get A is equal to V minus V0 or delta V. That works as well for most people. And you divide this by T. So you can and you get your acceleration is -2 meters per second squared. Since you know your A, you can use the we can use our newly found A as well as V initial and time to use, and we can use the third kinematic equation. Delta x equals to V initial t plus 1/2 of AT squared. Substitute in your values and compute, and you can get that the car, while decelerating, travels 16 meters. Okay. A moving object slows down its motion from 12 meters per second to rest at a distance of 20 meters. Here, we don't have a V final, so you cannot just use the first equation like we did in the last problem. You have to, again, assess your situation. Here we're given your V initial, your V final, and then your displacement. And your so you need to use your fourth kinematic equation for that, because that's the only one that actually has A in it and also has the other 3 variables that you already have. So here we know delta x is 20, V final is 0, and V initial is 12 meters per second. So you can plug this in, and then you get 0 equals 144 plus 40a, and then you just solve that equation for a, and you should get a is equal to -3.6 meters per second squared. Here we could use this because, again, this is basically, it only works for constant acceleration. So in more advanced physics classes, you have to take note of whether you know your acceleration is constant. For example, if you are like spinning something around, if it's for like if it's rotational motion, you cannot use these equations because your acceleration is not constant in that kind of situation. So again, context is always important. Okay, our next one is a bullet leaves the muzzle of an 84 centimeter rifle with a speed of 521 meters per second. Find the magnitude of the bullet's acceleration by assuming it is constant inside the barrel of the rifle. So again, you can use your force kinematic equation because you have this is your delta x, your displacement, your V final, because this is the speed at which it leaves. We know that before you fire a gun, the bullet isn't moving within the gun, so your V initial is 0. You also would know that. So you already have your 3 variables you need for this force kinematic equation, and you can again just simply solve for A. So you plug our numbers, you can plug the things in. 521 squared is equal to 0 squared plus 2A times 0.84. You get this, and then you solve for A, which yields an answer about 1.62 times 10 to the power 5 meters per second squared. Here we're using this notation because it is with proper sig figs and significant figures, so it means the measurement is pretty accurate relative to what we might observe in real life. And it's an extremely large number, so it's not good to just have to like write that out completely. It's easier to use what we call scientific notation, which is just relating things to powers of 10 in multiplication. A car starts its motion from rest and uniformly accelerates at a rate of 4 meters per second squared for 2 seconds in a straight line. So we know from the word from rest, we know V initial is 0. So we can put it as that. We know A is constant because the word uniform is there. Uniform here means that the acceleration is constant. So we can denote this as A. Basically, A is a constant, and we are later given this value, and it is 4. We also are given T, so it's 2 seconds. So we know V0, A, and T. So the equation that would relate this would be your third kinematic equation. So delta X, what we're trying to find in part A, how far did it travel? That's the displacement. This is equal to V0 T, V0 T, plus 1/2 of AT squared. So you can just plug everything in on the right side because we're given everything there, and you get delta X is equal to 8 meters for part A. What is the car's velocity at the end of that time interval? One way you could do it is to use the fourth kinematic equation. So you would use V final squared is equal to V0 squared plus 2A delta X. You can also use the first one, which is way easier. So you would just use V is equal to V0 plus AT. Oh, sorry. Plus AT. Because you're already given basically, once you solve part A, you already know all 4 variables. V initial, V final, A, and T. And then X as your fifth. So you're already given everything. So you could just use this first one. It's a bit easier to do since V initial is 0 anyways. You get the same answer that V would be meters per second. So it doesn't matter. They produce the same answer. It might be just easier to go this way though. Okay, so that's it for today. Do you guys have any questions or anything? If you want, I can explore a bit further into like these kinematic equations and like why that works. And we can also go over some practice problems if you want. Uh, oops, sorry. Okay, since Alice wants to would like to do some practice problems, I'll try to pull some up. Our time is kind of limited though. Maybe we'll just do 1. Okay, so I pulled up this worksheet on kinematics. So let's wait for it to load. So the first question in this worksheet asks which of the following is a kinematics variable: displacement, time interval, constant acceleration, or all of the above. So we talked about our basic equations, right? And one of the most common ones that we used was the third kinematic equation, the one that related distance, initial velocity, and acceleration, as well as time. So from that, we know that delta x, or displacement, is equal to v initial t plus 1/2 of at squared. And then that would be equal to, so then we know that within this equation, displacement, your change in time, as well as your acceleration, all appear. So the answer should be all of the above, which is correct. The next one. Ball is released from the top of a tower of height h. It takes t seconds to reach the ground. And then what is the position of the ball in t over 3 seconds? Actually, that one, you could do it without using kinematics if you studied like energy or something. So, but here you would have to know that your acceleration is g, so is a gravitational constant for Earth. Since we're assuming this is from Earth, your gravitational acceleration from the center of the planet is about 9.81 meters per second squared. So you would have to multiply it out and just solve. A ball is thrown vertically downwards with a velocity of 20 meters per second from the top of a tower. It hits the ground after some time with a velocity of 80 meters per second. And then they're asking the height of the tower. So basically, what distance did the ball fall? And then we are assuming your g, basically the gravitational acceleration, is basically from the planet pulling down the ball. We're assuming it's equal to 10, since that's an approximation of 9.8. So here you would use your third kinematic equation. So basically, when they say thrown downwards with a velocity of 20 meters per second, that would mean that your initial velocity is 20. And then doesn't really matter what t is here, because we know what v0 is. We also know what a is. A is g. And we also know what VF is. So we can use actually that fourth kinematic equation and just be able to solve that. And then if you do that, you would get the answer would be 300 meters for the height of the tower. So that's kind of like some uses of kinematics in general. I think I'll wrap it up here though for today. If you have any issues, or if you want further practice problems, you can contact me after this lesson, and I'll be happy to email you some of those. But for now, I guess I'll see you in the next time that we're going to do a workshop for LogicStem. So until next time.